Hello everyone, I am Akanksha from Sri Venkateshwara College of Engineering. Today I am going to discuss about the topic DFA and NFA in the theory of computations. So the introduction to DFA and NFA. DFA and NFA are fundamental concepts in automata theory. They serve as abstract machines for recognizing regular languages. Understanding the difference is essential for computational theory. The definitions of DFA and NFA. A deterministic finite automation has a single unique state transition for each input symbol. A non-deterministic finite automation can have multiple transitions for the same input symbol. Both DFA and NFA can be used to recognize the same class of languages known as regular languages. So, what is meant by finite automata? A finite automata are mathematical models used to represent and control the behaviors of systems with a finite number of states. They are essential in computer science and linguistics for modeling and analyzing various computational processes, particularly those involving pattern recognition, text processing, and control systems. Automata are a type of abstract machine with a finite number of states. The transition from one state to the next based on input. Since a finite automation has no temporary storage, it can only remember a limited amount of information, relying solely on its finite control, which consists of states and transitions. What are the key components of finite automata? The first one is a state, a finite set of conditions or configurations the automation can be in. One of these states is the initial state where the automation begins, and one or more may be accepting or final states where the automation successfully terminates. The second one is the alphabet. The alphabet, it is a finite set of symbols or characters that the automation reads as input. The next one is the transition, a set of rules that dictate how the automation moves from one input to another state based on the input symbol it reads. This is often represented as a transition table or a state diagram. The next one is the acceptance. A string is accepted by the automation if, after reading the entire string, the automation ends in an accepting state. What are the formal definitions? A DFA is mathematically as a quintuple of Q sigma QF and F. It is a five-tuple notation where the Q is the set of final state. Sigma is an input alphabet that contains a finite number of input symbols. The next one, it is the transition function defined over transitions of FA for state and input. Q naught is the initial state or the state of FA, and the next one last is the F is the set of final states of FA. Finite automata are divided into two categories. That one is NFA and a DFA. And NFA is similarly defined, but it includes e-transitions, allowing transitions without consuming input. These formal definitions provide the foundation for understanding their operational differences. State transition diagrams. DFAs and NFAs can be represented using state transition diagrams. In NFA, each state has exactly one outgoing edge for each input signal. In contrast, NFAs can branch into multiple states for a single input, illustrating their non-determinism. In NFA, for every valid string, an NFA ensures at least one path from the initial state to a final state. Unlike a deterministic finite automation, an NFA does not require transitions for invalid combinations and may include empty string transitions, where the automation can change states without consuming an input symbol. Although NFAs are generally less efficient in processing input strings than DFAs, and NFAs can be converted into an equivalent DFA. In the DFA, for each state and every input symbol in the alphabet, there is exactly one possible transition state. This characteristic distinguishes it from other types of automata, making it a deterministic finite state machine or deterministic finite acceptor. A DFA processes both valid and invalid strings in a regular language, ensuring that all valid strings lead to final state and all invalid strings result in a node final state. Each input string produces a unique predictable computation or an enabling the DFA to be fully automated. Equivalence of DFA and the NFA. DFAs and NFAs are equivalent in terms of the languages they can recognize. For every NFA, there exists a corresponding DFA that recognizes the same language. The conversion process from NFA to DFA is known as the subset construction algorithm. Computational complexity. DFAs can be more efficient in terms of time complexity during execution. NFAs may require fewer states than DFA counterparts for the same language. Research has explored the trade-off between state complexity and computational efficiency. Applications of DFA and the NFA. DFAs are widely used in the lexical analysis for programming languages. NFAs are often utilized in pattern matching algorithms such as those in text editors. Understanding their applications helps bridge theory with practical computing solutions. What are the limitations of DFA and the NFA? DFAs require more memory for larger language representation due to state explosion. NFAs can be less initiative to implement in certain computational scenarios. Both automated types have limitations in expressing context-free languages. Recent research trends. Recent research studies found on optimizing conversion algorithms between NFAs and DFAs. There is ongoing research into minimizing state complexity in practical applications. Their exploration of hybrid models combining NFA and DFA characteristics is gaining interest. So the main difference between the NFA and DFA is a DFA transitions into exactly one ensuing state for each input. So as the NFA means it is the finite acceptors but use different approaches to reach the final states. So DFA and NFA are crucial for understanding computational theory and language recognition. Their equivalence and differences offer deep insights into automated design and efficiency. Continued research in this area promises advancements in both theoretical and practical computing. Feel free to adjust any of the content or the structure to better fit the presentation style or audience. Thank you.